Yeah, thanks for having me here. Today, I'm going to talk about a topic that I am particularly excited about, which is getting AI to do things that I can't, scalable oversight via indirect supervision. So before we dive into the technical detail, let's first look at a very broad overview of AI research. There are, broadly speaking, two sets of tasks. There's a set of tasks that humans are good at, and there's a set of tasks that we want machines to be able to do. So typically, in the past few, or say like 5 to 10 years ago, when we propose new NLP tasks, we typically take the intersection of the two, which is known as automation. So for example, spam classification, grammaticality check, sentiment classification, paraphrase detection. These are the things that humans are relatively good at, and we want machines to be able to do that as well. In all of these cases, we use imitation learning, where we collect a lot of human labels, and then we train AI systems to mimic human labels, and we evaluate AI systems based on whether they agree with human. So this works pretty well. However, it will be a waste of our opportunity if we only focus on this intersection, because there are a lot of things that I want AI systems to be able to do, but I am not good at. So in particular, here's my wish list. I want AI systems to be able to augment me, to be able to discover patterns in the data that we haven't noticed before and explain that pattern in natural language. I want AI systems to generate complex programs that I cannot directly understand, but can still fulfill my intention. I want AI systems to help me predict the future. I want AI systems to help me design and run experiments. So it would be great if we can build AI systems to do that. However, it is unclear how we're going to supervise AI systems to do that, because imitation learning no longer works here. Suppose that humans are not good at it, then we shouldn't ask AI systems to mimic human. Then the main question that I'm going to talk about today is, how can we supervise AI systems even when we humans struggle to verify that it is correct? Well, unfortunately, I do not have a general answer to this, but we do have reasonable attacks to the first two problems on this wish list. The first task that I'm going to talk about is describing distributional differences. The input to the AI systems is going to be two large corpora. So for example, patient feedback for drug A, patient feedback for drug B. And then you have two large corpora, and our AI systems will take in two large corpora and generate a natural language description of how they are different. So for example, patients more often have strong feelings of paranoid after taking drug A. The second task that I'm going to talk about is, given a natural language question, we wanted to produce a very complex program that can fulfill that intention. And in particular, in this work, we are interested in how do we enable people who do not understand SQL to be able to supervise AI systems to write complex SQL programs. In both of these cases, we notice that imitation learning is probably not the great idea, because even experts are far from perfect doing these tasks. And by the end of this talk, I'll show that it is indeed possible to build AI systems that can discover patterns between the difference of two large corpora that experts did not notice before. And also, it is possible to supervise AI systems to write complex SQL programs just based on the feedback of people who do not understand SQL. And in fact, we find that in one of the most popular semantic parsing data sets, our system finds that there is 25% of the annotation mistake by the previous database experts. So how do we do that? In this talk, I'm going to talk about the framework, which I call propose and reduce. At the top, so these three items are different supervision framework. At the top of the screen is our most familiar supervision framework, which is imitation learning, where the human annotator will write the full output. And at the bottom is going to be our approach. And to move from the top, which is imitation learning that we are familiar with, to the bottom, which is our approach, it requires two conceptual advances, which is propose and reduce. The first conceptual advance, which I'll call propose, has already happened. Instead of asking human annotators to write the full output, we are going to ask AI systems to propose multiple different candidates based on the user input. And then what the human annotator need to do is just to directly verify which one of the output is correct. So for example, instead of asking human annotators to write the full dialogue response, we can simply ask human annotators to pick one of the best dialogue response proposed by the AI systems. Instead of writing the full explanation, we can just verify which one of the explanations is best. Instead of writing the full summary, we can just ask annotators to pick the best summary. So this intuition is analogous to P versus NP. So there are a lot of problems that are computationally challenging. It is hard to write the answer yourself or search for the answer yourself. However, if there is another system that proposes a solution, it is easy for the human to verify that the solution is correct. Okay, so that's the first conceptual advance which is proposed. However, we are not quite there yet to get AI systems to be doing arbitrary things that we want, because for many tasks that we care about, it is still extremely hard for human to verify that it is indeed correct. So for example, how do we verify that a corpus level description is correct? Human needs to read the entire corpus to reach the conclusion. How do we enable people who do not understand source code to verify that the source code is correct? How do we verify that the book summary is correct? So in this talk, I will develop a second step, which is called reduce, where instead of asking humans to directly verify which output is correct, we are going to ask humans to indirectly verify which output is correct on some easier forms of problems. So for example, instead of asking humans to read the entire corpora, we can ask humans to examine individual samples and then later ensemble the result together. Instead of asking humans to read the source code, it is much easier for them to read some simple to understand test cases. And instead of asking humans to read the entire book summary, perhaps it is easier to summarize subcomponents and verify the summarization for the subcomponents and then recursively combine them together. So that's the overall framework. And now I'm going to talk a bit about the outline of today's talk. I'm going to talk about two tasks: discovering and describing distributional differences, supervising code generation models with non-programmers, and I'll talk about the future work. Some of them are my conjecture about where the field is going, and perhaps some of the hot takes to provoke discussion. Cool. So the first part of this talk will be discovering and describing distributional differences, and for reference, this is based on these three papers. This is a fairly new task, so let me introduce the setup a bit. The input to the AI systems is going to have three components. The first component is the research context. I am an educator. I want to understand how different students write essays differently across schools. And the other two components are two large corpora. Corpus A, students' essays from school A. Corpus B, student essays from school B. Given this input, we are going to map it to a natural language description of how they are different, which is also related to the research context. So for example, the output could be student essays from school A use numbers and statistics more often. So why do we care about this task? It turns out that a lot of important applications can be reduced to this task. So for the first example, suppose that you're interested in distribution shift. There's the training data, and there's the actual data you get from deployment. Then you can try to describe the difference between the user's query, which is the data you get from deployment, and your training data. And our system might say that at deployment time, there are more queries that contain more slangs. If you're interested in politics, you might be able to describe the difference between Obama's speech versus Trump's speech. And you might find that the former are more supportive of immigrants. The third one is more related to nowadays situation where there are a lot of text that are being generated by machines, and it is important to figure out how human perceive those text. What are the kind of text are perceived to be human written, and what are the text that are perceived to be machine generated? And so you can also apply this system, and then our system finds that text perceived to be human written contain more personal experiences than those perceived to be machine generated. So there are a lot more applications that I won't be able to have time to go into detail today, but just to let you know, this seems to be a pretty generally useful tool. One mental model here is that whenever you use logistic regression to compare two different corpora to do data exploration, you can apply a similar tool here, and then that will give you a natural language description about how they are different. However, if we want to build AI system to do this task, it is unclear how we are going to do this yet, because imitation learning doesn't work. This is a difficult task, and typically the two large corpora might have thousands of samples, and it is extremely time-consuming for people to actually read the two large corpora and say the orange text mention more female entities, which is also a subtle difference that a lot of people might not be able to find out if they do not read carefully enough. So to build AI systems to do this task, I'm first going to introduce some of the notation, and then I'm going to describe the method. Just a reminder, the input is a research context described in a natural language string. I want to understand student essays. And then there are two large corpora, which I call distribution A for corpus A and distribution B for corpus B. Given the input, which consists of the research context, distribution A, distribution B, we are going to map it to a natural language description as use numbers and statistics more often for distribution A. And notice that in this talk, I'm only focusing on correlation, and we cannot draw any causal conclusion from this. So for example, it does not imply that if you write essays, use more numbers and statistics, you are more likely to be admitted by school A. Or if you go to school A, the teachers will tell you to use more numbers and statistics. We are only focusing on correlation. Cool. And this is going to be a hard task because each of the two large corpora might have tens of thousands of samples. To do this, we are going to take the two-stage recipe that I have just talked about. The first stage is going to be called propose. What we did there is we construct a large prompt where we first feeding the model with a lot of samples from distribution A, and then a lot of samples from distribution B. And then append the research context. I want to understand how students write essays differently. And then ask language model, how are the samples from distribution A and distribution B are different? And then the model can propose multiple different candidate descriptions. So for example, is offensive in tone or use more statistics. And then what is left to do for human is to verify which one of the description is correct. So one way to look at this is you're just going to ask language model to brainstorm a lot of different hypotheses, and then you're going to ask someone else to validate these hypotheses and whether they are true. Cool. However, it is still hard to verify that the description is correct. So, because humans might not have the time to read the entire corpora. So we apply the second stage of the recipe, which is called reduce, where we reduce the problem of verify a description on the entire corpora of DA and DB to a problem that is easier, which is verify that the description is valid on individual samples, DA and DB. And then later combine the results on individual samples together. To make it concrete, here is how we are going to actually evaluate how valid a description is. So suppose that we want to evaluate the description as samples from DA uses numbers and statistics more often. What we'll do there is we are going to take two samples from the two distributions respectively, and then we'll give it to another human. The other human actually does not know which one of the xi and xj is coming from which of the DA and DB, and they can only guess which one of the sample is coming from which distribution based on the natural language description. So in this case, the human will guess that xi is from DA and xj is from DB because the description uses numbers and statistics more often, and xi happen to have some statistics in it. And then we can calculate the loss of the description S, which is how accurately humans can use S to guess which one of the sample is from DA and which one of the sample is from DB. So just to summarize, the quality of the description is how accurately it can enable another human to tell a random sample whether it is coming from whether it is coming from corpus A or corpus B. So this is going to be how we operationalize this evaluation. Suppose that we have infinite budget. However, very unfortunately, we do not have infinite budget because if you want to have a high accuracy estimate for how often human makes mistakes on classifying DA and DB, that is going to take you a lot of money. Like in this paper, when we try to do this evaluation, we repeat it 100 times, and then each of them takes actually $10 to evaluate. So this seems to be a bit unscalable. So we did something that can make verification more efficient, which is instead of asking human to verify on individual samples, we ask machines to simulate the human's judgment. And it is much cheaper to calculate the error rate of a model than to calculate an error rate of a human. So to recap for the method, this is to combine the two propose and reduce stage together. We will first propose descriptions with GPT-3 or potential GPT-4. And then we will reduce the verification problem of the description to examining individual samples, which is more tractable for human. However, it can still cost a lot of energy for human. And later, we make the verification more efficient by simulating humans with machines. And to show that our method is successful, we will compare the quality of the description after reduced verification to the top one candidate or a random candidate proposed by GPT-3. So this means that after applying our reduction method, the quality of the description should improve. Cool. So now let's look at some benchmark results. So here we are going to have a collection of binary classification tasks, and then what we are going to do is to feed in the samples with label 1 and the samples with label 0, and then ask the system to recover the natural language description about what this task is. So for example, for a binary task classification task of sentiment classification, then we will feed in a bunch of samples that are positive movie reviews and feed in a bunch of samples that are negative movie reviews. And our system should be able to tell that DA contains more sentimentally positive movie reviews. And here is the result. Suppose that we just take a random description that is being proposed by the language model. The accuracy is only 7%. However, after applying the reduced verification, the accuracy is 31%. And notice that this research has been done around 2 years ago. Well, 2 years ago. So right now, I think for GPT-4, it can just directly crush this benchmark. Cool. So this is the benchmark result. And now let's put it into practice to see whether they are actually useful. So the first application that I'm going to talk about is dataset misunderstanding. So there is a dataset called subjectivity analysis dataset. And then, so the dataset setup is that there are a bunch of text and they're grouped into whether they consider the text to be having subjective opinion or it's an objective description. And at least 4 different papers use this dataset in this way. So we feed the objective text and the subjective text into our system. And our system says, as the description that can discriminate the 2 large corpora is that DA is a plot summary of a film. So back then, we were super surprised because why would a system make such a mistake? And it turns out that it is not the system making the mistake, it's us making the mistake. Because when we look at the original paper, which proposed this dataset, they say that to gather subjective sentences, we collected movie review snippets, and to obtain mostly objective sentences, we take 5,000 sentences summaries from IMDb. And then, so this surprises us a bit because we didn't even notice that the dataset was collected that way. And we contacted 4 other papers author who use that data set, and none of them actually noticed that the data set was being constructed this way. Another example application could be describing distributional differences between a natural language inference data set. So for example, if you're feeding the natural language, if you're feeding the data points from SNLI and compare it to the data points from MNLI, then our system have the natural language description. It involves physical activities such as walking, playing, climbing, or biking. And one potential explanation for this is that SNLI contains sentence-based picture portraits, while MNLI has multiple different genres. So for example, speech and fiction. And perhaps in pictures, it is easier to see people having actual physical activities than, for example, looking at text where people are just talking about stuff. We can also use this to understand what errors the models are making. So the example task that I'm going to study about is what inputs cause a model to fail. And the task here is zero-shot classify whether an argument supports a claim. So what we did there is we gathered a bunch of data points where model A misclassifies the label as support, and a bunch of data point where model B misclassifies the data point as support. And then if we compare the differences, we find that model A, the errors that the model A make are more likely to use language that are positive or uplifting. One potential explanation for this is that model A might have misunderstood support as a sentiment label, the support in the natural language instruction as a sentiment label rather than a logical relation. So far, I have covered 3 example applications in machine learning, exposing dataset misunderstanding, describing distributional shift, and analyze model errors. And there are potentially more applications. So for example, debugging dataset shortcuts, explaining human preference, compare language model generation, and blah, blah, blah. And this is only restricted to machine learning. And in fact, if you look at things more broadly, there will be many more applications. So for example, health, compared to different doctrinals of different diseases, humanities, business, social sciences, etc. And in our latest paper, we collected a data set which have around 600 of such problems. And if you're interested in what are the other applications, you can check out our paper. So to sum up, for the takeaways of task 1, the setup is we're going to describe distributional differences, and this is a hard task even for human experts. And the method that we're going to use is we first ask GPT-3 to propose the descriptions, and then we reduce the verification problem to examining individual samples. And finally, to make verification more efficient, we simulate the human verification on individual samples with machine sometimes. And as we can see, our AI systems is able to discover insights that even human experts did not notice before. So that's the end of the first task. And do people have any brief clarification questions?
How do you get the initial sets of proposed descriptions to the task?
Wait, sorry, I didn't hear that. Can you say it again?
How do you get like the initial sets of proposed descriptions?
How do I, okay, so suppose that I look at this, which part are you referring to? It's the initial.
For example, how do you get like the machine to first propose like a set of options such as like is offensive in tone, uses more stats and stuff like that?
Okay. Yeah, so yeah, we just feed this prompt to GPT-3 and then it will
okay.
Prompt, right?
Gotcha.
One more question. The propose and reduce feedback mechanism that you mentioned, it seems very similar to the RLHF mechanism that is used. I'm not sure if I understand what is the difference between in the sense both rely on getting human feedback and then tuning the systems. to generate better outputs. What would be the, in your opinion, the major difference between RLHF and reduce, propose and reduce?
Yeah. So if I understand correctly, you're asking what are the main difference between RLHF and my proposed method. I would say that this method is still based on RLHF, but we need to have an additional step of reducing reducing the problem to something easier, such that human can provide more reliable feedback. So for example, here, I'm reducing the problem of verify a description on the entire corpora to verify that the description is correct on individual samples. So yeah, so in RLHF, like usually people have the mindset of, okay, we can just ask random people to give you the feedback. However, if the task is really hard, first of all, random people might not give you the best response, and sometimes even expert will not be able to give you the right response. So instead of making, so to make it easier for humans, we'll have to do something else.
Follow up on that, like how do you select the individual samples? Is there some sort of algorithm you use to make it representative of the whole corpus?
Oh, yeah, so that's a very good point. For evaluation, so for this evaluation, we are actually just taking random sample from the two distributions. However, here in the paper, what we did here is we first suppose that we want to construct a proposer prompt to help the language model to propose better descriptions. We first use train a classifier to predict which sample is coming from which distribution, and then we mostly focus on the data points that are more representative or more representative about the two distributions, and then prompt the language model. So you can imagine that like there is a corpus with black sentences and white sentences, and then we are ruling out all of the gray sentences, and then we just take the two polar to prompt the large language model.
Gotcha, thanks.
Cool.
I have like one random question. So in one of the binary classification tasks, the baseline was 9%, and then the improve was 31% or something like that.
Yeah, right.
That's a binary classification. Why did it?
Oh, sorry. So here, I'm trying to find the slide. Sorry. The task is not binary classification, but we used 54 binary text classification tasks and then try to see whether they can recover the underlying text description. So out of 54 binary text classification tasks, we can recover the underlying text description of the binary text classification task 31% of the time. All right, so cool. I will talk about the second part of my talk, which is supervising code generation models with people who do not understand programming. And for reference, this is based on these two papers. The task that we're going to study is semantic parsing, where you have a natural language question, and then you're going to map it to a SQL program. So for example, how old is the youngest person from department A? And then you're going to produce a SQL program, select minimal age from people where department equals A. So it is extremely expensive to collect expert annotation because you're going to hire people who know programming. So the question becomes, how can we enable people who do not understand programming to supervise models to write complicated SQL programs? So we can still apply this framework, which we call propose and reduce. So given a natural language question, how old is the youngest person from department A, we are going to propose multiple different SQL candidates with a large language model. So in this case, Codex. And then Codex will propose multiple different candidate SQL programs, each of them being associated with a natural language, a probability score. And then what we are left to do is to enable people who do not understand SQL to verify which one of the SQL program is correct. So you might think that this seems to be an easy task because, well, youngest person will correspond to minimal age, department A corresponds to department equals A. So in this case, it's actually pretty clear-cut. But the general case is pretty hard. And this is one example. Find the first name of students who have both cat and dog pets. And we want people who do not understand SQL program to choose between candidate SQL program that is this long. And in particular, they are going to choose one of the 32, which is also pretty hard for an expert. And I'll then talk about how we can enable people who don't understand SQL program to be able to do that. So instead of asking people to directly verify which one of the program is correct, we reduce the problem and ask people to verify that a program has the right behavior on some example test cases that are simple to understand. So in particular, how we operationalize this is, suppose that we have an actual language question, suppose that we have multiple different SQL programs, then let's assume magically there's just this database coming out of nowhere. But suppose that this database exists, this is a very simple table that people can understand. And then we can ask people who don't understand SQL to answer this question on this database. And then we can execute the SQL programs on this database as well. And as a result, we can see that we can compare the program's execution result to the non-expert's answer, and then we can figure out that the first two SQL programs disagree with the non-expert's answer, and as a result, we can rule out the incorrect SQL candidate. So it seems to work. However, we haven't talked about how we can choose such a database yet. And that is going to be the focus of the next part. So how do we pick such a database? One intuition that we need to employ here is that we want to maximize the bits of supervision with minimal human effort. And we want to choose a database such that its size is small, however, its information gain is large. For the first criteria, we want the database to be small. Just imagine that we choose a database that is around like 1,000 rows. And then suppose that we give this large database and the question to an annotator, they might spend like 2 hours without even, and they might make a lot of mistakes on this. So that is not ideal. And the database input must be simple enough to comprehend. The way to formally write this is that the size of the database should be small. And here we are defining the size as the number of rows in that database. And size is a mapping, or say function, mapping from the database to a real number. So that's the first criteria. However, that criteria is not quite enough. So for example, this is a database that is pretty small. However, it is still not ideal because suppose that you answer this question on this small database or execute the SQL program on this small database, you'll find that all of the answer is the same. As a result, you are not able to rule out any of the SQL program if you just present the annotator with this small database. So this is not informative, and then we are simply wasting the annotator's time to provide an answer that cannot rule out any of the SQL program. But to formalize what we want, let's assume that we have 3 SQL programs and we have 3 probability scores. Each of them is 1/3. And then they lead to different execution results. And remember, we want the answers to be as diverse as possible, because suppose that each of them have different answers, then as long as we get the answer from the non-experts, we can rule out all of the rest of the SQL programs. And we formalize this with entropy, where we calculate the entropy of the execution results of the SQL programs. And in this case, the entropy of the answers is going to be 0.92 bit. As a result, we can say that the information gain of this database is 0.92 bit. And again, information gain is another function that maps from a database to a real number. And also notice that the information gain function also depends on the probability distribution of the SQL programs provided by Codex. So now we have 2 functions of the database, and then we can try to optimize the database based on these two functions. So we are going to optimize the database such that it has as high information gain as possible, but still under a size constraint. And in our case, we require the database to only have at most 15 rows. There are a bunch of technical details that I won't be able to cover in this talk, but we use fuzzing to generate large databases with large information gain. And just like fuzzing is a software engineering term where we're just generating a large number of random test cases and throw them at a program to test its behavior. And then we're going to drop the rows greedily to decrease its size. And sometimes one database of interaction is not enough to rule out all of the SQL programs. So we did a multiple round, synthesized multiple database, and then asked annotators to provide an answer for each of the database. Cool. So here, to recap for the method, here is a recipe, which is propose and reduce. We first propose the SQL programs with codex. And then because it's hard for people who don't understand SQL to verify which one of the SQL program is correct, we reduce the verification problem to examine the answers on the databases. And finally, we make the verification more efficient by making databases small and informative. One way to look at this is you're going to, given a natural language question, you're going to just randomly come up with different programs, and then you're going to come up with small test cases to debug which one of the program is correct. And then you choose which one of the program is correct by looking at your test output. And the victory condition here is after reduced verification, which is interacting with the non-experts, the accuracy of the program or SQL program should be better than the top one candidate proposed by the AI system. So in other words, non-experts plus AI systems should outperform AI system alone. Now I'm going to talk about the actual data set and the baselines and the general setup. So just to recap, we have a natural language question. We are going to propose multiple candidates with codex, and then each of them has some probability score, and we take the one with the highest probability, and which is codex top one. So this is a purple. So this is what we call the purple baseline, where we simply take the most confident output of the AI system. Then we do our reduced verification, interact with the non-experts, and then we can obtain another candidate, which is shown in blue here. And we call this to be non-expert annotation. And in our human-computer interaction experiment, we recruited 11 students who have no CS experience, and we confirmed that they have 0 SQL experience as well. And the victory condition here is that the blue should outperform the purple. However, here's one tricky thing, which is how do we even define the ground truth, which is a reference that we need to use to check whether a program is correct. So there are several different ways to establish the ground truth. We could use prior expert annotations, which is database experts. But we suspect that the previous annotation was noisy. So we established our new gold standard by our authors using our system and to get the annotation. And then we also check the SQL directly. We compare with the previous annotation whenever there's disagreement, and always favor the previous annotation if there are ambiguities. And finally, we discuss with the previous annotators for every single change that we made. So that's how we are establishing the gold standard, which is a combination of AI systems plus many different experts from different teams. So now let's look at the result. Codex top line accuracy is 59%. And if we use a non-expert to interact with the AI system, then we have 75% accuracy. So this still has a lot of room for improvement, but it is much better than if we simply take the AI system's best output. And what is actually most interesting is that when we look at the annotation from previous database experts, it's also only 75%, which is on par with non-expert annotation using our AI system. So we might wonder, what are the kind of mistakes that the previous database experts made but we actually are able to identify with our AI system. So here is one example, and this is the one example that I show you, which demonstrates that it is actually difficult to verify which one of the program is correct. And in fact, one of the experts wrote the SQL program in red, which is wrong. So I will first talk on a very high level what these two programs does. So find the first name of students who have both cat and dog pets. The first SQL program will select the students who have cat, select the students who have dog, and take the intersection of the students, find the first name, which is correct. What the expert wrote here is actually a careless mistake, where they find the first name of the student who have cat, first name of the student who have dog, and then take the intersection. It is not quite obvious why this will fail, but suppose that you have an example, then it is easy to see that it is failing. So in this case, you have two students, Alex Pan and Alex Wei. Alex Pan has a cat, Alex Wei has a dog. What this expert written SQL annotation did here is they'll first find the first name of the student who have cat, which is Alex. They will find the first name of the student who have dog, which is also Alex. They take the intersection of the two, which is Alex, and concluded that Alex have both cat and dog pets, which is wrong. So this is a subtle mistake that you won't be able to easy to tell unless you have another AI system to propose multiple different candidates and also try to find a simple and easy to understand test database to run your SQL program on. To summarize the takeaways of the second task setup, we are going to enable non-experts to label complex SQL programs. And the method that we're using is we're going to propose SQL programs with codecs. We're going to reduce the verification problem to examining input-output examples, and we are going to make it verification more efficient by maximizing the information gain under some size constraint. And we are able to discover that the previous data set has at least 25% of the annotation mistake. So that concludes the second part of this talk. And do people have questions?
Hi. So this proposed model is for SQL programs, right? So suppose how would you scale it for non-SQL programs with no database, like normal coding problems? How would you use the propose and reduce method and use the evaluation to verify if the labels are correct or not?
Yeah. So I guess if we want it to be more generalized, then there are many different modifications that we need to make. So for example, extending SQL program to any other programming language, then you'll have to have some way to synthesize the program input. So for example, suppose that you want to synthesize a Python function, then you have to have some method to synthesize an input to that Python function and then run it. I would suspect that current language model, for example, GPT-4, can already do a decent job of coming up with these test cases. And then what we need to do is to choose which one of the test case is most informative and also have the least burden on the annotators. And suppose that we want to push it further, we might realize that not every code context actually can be directly executable when you develop something. So in those cases, suppose that the program is huge, then we might need to consider decomposing the large function into different components and test them one by one. Or in some cases, we might need to introduce some other information. So for example, reduce the program verification problem to something like, did the program use certain keywords that the user know that the keywords should present, or reduce the problem to, does the program provably satisfy certain properties? So this is, I think, a pretty open direction, and just let me know if this answer is helpful.
Yeah, it's helpful. And I have one more question, like to generate those SQL programs, do we have to run the code gen multiple times to give different ways of answering the questions?
Do you mean the proposing step, or?
Yeah. Proposing multiple codes, yeah.
Yeah, so here we show that we run the language model for like 32 different times. to generate 32 candidates. And actually what's happening there is much more complicated in the paper, where we actually sample like 2,000 times, and then we merge the semantically equivalent SQL programs. And then we only take the top 32 semantically equivalent class. So that's what's actually happening on the under the hood. And I guess in the future, to make it more efficient, you could potentially just ask language model, hey, just directly give me 3 different SQL programs that are different that can solve this, that could potentially solve this problem. Just give me 3 options.
So can I understand this as if we have enough test cases, then we might be able to like improve it even more in the non-expert annotation case?
Oh yeah, definitely. So suppose that we have infinite number of test cases, and suppose that the human annotator can actually choose which one of the answer is indeed correct. Then indeed we can figure out the ground truth program. However, on the other hand, there are a couple of failure modes that I actually haven't covered in this talk. So for example, suppose that we ask the program to say, show me the entire program, but only show me the entire database, but show me only the top 100 rows of the database. And in order to verify that the subpart of the top 100 rows, you actually need to produce a database that has more than 100 rows to test that branch. So that could be one potential failure mode. And some other criteria of code might not just be execution correctness, but also things like readability or like efficiency, etc. And these are the cases that my current method is not able to cover. And I guess that's a lot of future work to do there as well. So future work, which is where I conjecture where the field will be going, and also some of my hot takes, and it is meant to be more speculative and provocative. The research direction that I'm describing is scalable oversight, which is what I'm focusing on right now. And the motivation is that suppose that we want to build AI systems that can augment humanity, then the main challenge is might actually not be the case that AI systems themselves are not capable enough, but the challenge is for humans to provide reasonable signal to oversee AI systems. And in particular, if these are the tasks that humans are not good at, then this could become an increasing challenge. The recipe that I'm proposing today is called propose and reduce. And then we make the indirect supervision more efficient by either simulating with human verification with learned models, and we maximize a bit of supervision with minimal human effort. For the future task, we might look at, for example, complex mathematical reasoning, and perhaps we can reduce the direct verification problem of checking whether the final answer is correct by verifying the decomposed steps. For machine translation, instead of asking humans to look at the entire sentence, whether it is correct, we might be able to just ask them to verify uncertain phrases, and perhaps it can decompose to simpler problems. And finally, we might want to develop a task-agnostic oversight framework. And it is not specific for machine translation or mathematical reasoning or describing distributional differences. And the reason is that these large language models are currently being proposed as general purpose tools, which people will use for almost arbitrary purpose. So this is a fairly new research paradigm, which is called scalable oversight. And the evaluation in particular is very tricky because we are going to evaluate AI systems under the circumstances where we humans might even struggle to determine the ground truth. So how to evaluate? So one mental model that you can have is that we can first establish the ground truth with a large or infinite budget. So that can include a lot of expert discussion and spending a lot of time, and then to establish a small subset of ground truths that we can trust. And then we can evaluate a proposed method with a small oversight budget. So suppose that a person spends very minimal effort to interact with an AI system and match the performance of a lot of experts spending a lot of time, then we can probably say something about the proposed method being good. For some further readings, I would recommend the paper Measuring Progress on Scalable Oversight for Large Language Models by Sam Bowman, who is currently on sabbatical in Anthropic. So this is a pretty young research area, and there are a lot of conceptual challenges and research opportunities here as well. And now I'm going to talk about some more provocative stuff. So we will probably see that oversight is pretty challenging. The current situation is that ChatGPT or Copilot, they actually produce highly plausible programs, stories, or explanations, and they usually outperform their average user on specific requests. So here is one example, which is in the Training the Helpful and Harmless paper. And so like I look at this example when I provided the feedback from their paper draft, and I said, okay, so what are the actual annotation mistakes in this example? So like it at least makes 3 factual mistakes: 270 electors, 48 states, and at least 250 electors. And unless you look at it super carefully, and unless you do have knowledge about US elections, it is very hard to tell that the model is making mistakes, especially because it is stating everything almost very confidently. And so these are the factual mistakes they tell me that exist in this response. And I actually pointed out one more, which is the model is claiming that it is doing a Google search, which is clearly not. So oversight is challenging for now. And if we look at the long-term trend, AI systems is going to be, oversight is going to be increasingly challenged. So right now we see that AI systems predictably acquire unpredictable capabilities. What I meant by that is for the past few years, every time we scale things up, we sort of observe that the model can do something else. So for example, in context learning, following instructions, or doing some planning in the context, blah, blah, blah. And because we have seen the models acquiring unpredictable capabilities in the past, we might be able to anticipate that it might acquire new unpredictable capabilities in the future. And just in case what you are wondering what happened for GPT-4, this is one favorite example that I have in one of the GPT-4 analysis paper, where they say we query GPT-4 3 times and ask it to draw a unicorn in TXZ. And this is actually a text-only model. And as you can see, it's a pretty cute unicorn. And yeah, and this was actually like completely unexpected for me. On the other hand, humans, we are actually granting greater power to AI systems. So for example, OpenAI is now piloting with plugins where you can connect it to your other apps, and it can allow language models to actually take actions in the real world. And there is a recent repo called AutoGPT, which basically just connect large language models to your terminal and then ask large language models to act as an agent to do whatever they want. And finally, humans as biological creatures do not evolve as fast. Yeah, so to summarize why we want oversight, and why we want scalable oversight, the reason is that human users and developers with at most slowly increasing oversight powers are granting drastically improving and unpredictable machine learning systems an increasing amount of autonomy and resources to take actions and perform increasingly complex and open-ended tasks at a planetary scale. So that's why we need urgently needs to empower humans to oversee machine learning systems in the coming decade. All right, so that's the end of the talk, and I would like to thank all of my faculty mentors and all of my undergrad mentees. And I guess we have 2 minutes for some discussions.